Dear jury members, this is the final project presentation of the group search team. You are all welcome. I am Atakan Severge and my project partner is Ataberkan Afşaroğlu. In the presentation, introduction of 2D materials, main purpose of the study, objectives of the study for this semester, applied methods and results, and conclusion statement will be given respectively. Two-dimensional 2D materials, also referred as single-layer materials, are crystalline materials consisting of a single layer of atoms. Thickness is neglected since it's smaller than 100 nanometers. With the exploration of the graphene, era of the 2D materials started. Recently, there are many studies to explore properties and applications of 2D materials. Calcium niobium oxide is the subject nanosheet. This nanosheet is obtained by exfoliating layered perovskite, potassium calcium niobium oxide, and it was successfully obtained in the form of solution last semester and reported as a first part of the study. This is supposed to be a surface-enhanced Raman spectroscopy application study. Normally, Raman modes of the small inorganic particles cannot be analyzed since the Raman modes of the particles are significantly weak. Purpose of the study is to enhance Raman modes of the calcium niobium oxide nanosheet by using gold nanopatterns and analyzing the effect of the gold nanopatterns of surface-enhanced Raman spectroscopy source measurements of 2D nanosheet. Focused on the purpose, objectives of the semester is given. Nanopatterning with nanospheres, monolayer coating of nanosheet, calcium niobium oxide nanosheet, source measurement, surface-enhanced Raman spectroscopy measurements. However, because of the pandemic situation, coating of nanosheet and source measurement couldn't be done. Design of deep coating system and design of vacuum chamber for physical vapor deposition was carried out instead. In the semester, nanopatterning method was applied. Nanosphere lithography was carried out together with spin coating and physical vapor deposition. And for design objectives, computer-aided design technique was used.
Deposition of materials in atomic size to obtain nanopatterns is called nanopatterning. There are several ways to perform nanopatterning. In our experiments, we carried out nanosphere lithography together with spin coating and physical vapor deposition method to obtain hexagonally packed gold nanopatterns. For obtaining a polystyrene nanosphere mask, we use spin coating. Spin coating is a procedure to deposit coating material onto spinning substrate to acquire thin films. According to literature we've done, parameters for spin coating were determined and coating operations were carried out. SEM images of coated mask will be introduced in the next slide. We can see there were monolayers in both coatings but in a tangled structure, and for 1/2 proportion had heavily uncoated areas that we did not want to. With solution of 1/3 proportion, there were again uncoated areas with monolayers on the surface of the wafer. When we look at the both proportions, we can see that 5000 rpm was not enough for polystyrene nanospheres to spread on the surface of the wafer. Therefore, we decided to increase the speed and time of the coating. Here, solutions of 1/3, 4, and 5 proportion, there were bilayer and monolayer structures formed together, while having uncoated areas more than one. With 1/7 and 1/10, the monolayers were formed together well, but the uncoated areas far too much larger due to overspeed of the coating. After the masking, physical vapor deposition was operated. With the method, source material is heated and its phase is changed to a vapor phase, and then back to a thin film condensed phase in a vacuum atmosphere. Having tested various parameters with spin coating, we passed to the deposition step with the most proper coatings and lifting the mask off from the gold particles. After the deposition of the gold particles and lift-off for 20 to 30 minutes, we can see that there were still nanospheres on the surface and was not removed well with the current lift-off stage. Here are the steps of before the gold deposition to total 57 minutes of liftoff respectively. Checking after 2 minutes of liftoff, we can understand the nanospheres were not fully removed and we continued to lifting off. After 10 more minutes of lifting off, there were still polystyrene nanospheres around and under the gold particles. Hence the structure starts apart in pieces. Lifting off for 45 more minutes shows that we were not successful on removing the nanospheres under the gold particles. And when we look at another example of before deposition to 30 minutes of liftoff, again, nanospheres under the gold particles were not removed properly. Then we decided to change the proportion of the solution from 1/7 to 1/9. After lifting off for 8 minutes, we saw that the same result with the others, which is non-removal of the nanospheres from under the gold particles. Another sample at the same parameters and it's lifted off for 15 minutes. We understood that 200 nanometer polystyrene nanospheres were not appropriate for our experiment. So we decided to increase the diameter of the nanospheres and changing our coating method to dip coating.
Dip coating is simple to apply and economical method to carry out coating operation. The method consists of immersing of a substrate in the pool containing coating material and then removal of the substrate from the pool and allowing it to drain. The coated piece can then be dried by nitrogen blowing. It is one of the methods for coating of the substrate with nanomaterials homogeneously. For incoming coating operation, dip coating pool was designed. According to the literature review about dip coating, pool was designed with 4 separate pools, each have different angled guide slider to be convenient general purpose dip coating tool. Teflon was considered first as a material, since it fulfills chemical resistance requirements with good smooth surface properties. After more material search was done, polyoxymethylene, known as Delrin material, was decided to work with, since it also chemical resistant and have smooth surface, but cheaper. Next is vacuum chamber design. Vacuum chamber was designed for physical vapor deposition with resistive heating. We focused on the cost effectiveness, functionality, and durability. Vacuum chamber will operate under high vacuum conditions, so it's very essential to tolerate the pressure forces and prevent any gas leakage. Cylindrical body geometry was chosen, since cylindrical body is stronger against pressure forces and requires shorter welding line. Chamber material was considered as 316L or 316LN steel. We avoid the design of parts with complex geometry and keep the parts easy to manufacture. It reduced the manufacturing costs. Most of the parts could be manufactured by simple sheet metal cutting and shaping operations. Chamber has changeable wafer holder. Put in wafer right at the top of the boat. Holder was connected to small interfacing welded on side wall with butterfly bolt. For resistive heating operation, ceramic coated cylindrical copper electrodes considered together with resistive tungsten bolts and ceramic metal composite shutter. For proper deposition, shutter must keep the source material inside the bolts until the material reaches required temperature.
Monolayer polystyrene mask was successfully obtained by spin coating method. Deposition of the gold particles with physical vapor deposition technique was done, however yielding of the gold particles on the mask was observed. Hence, lifting off was not successful due to the size of the nanospheres. Dip coating pool was designed and prototype was produced. Vacuum chamber for physical vapor deposition was carried out. Thank you for your attention.